A wood frog freezes solid every winter. I want to be precise about what that means because people hear it and picture something like hibernation. It isn't. Around 65 to 70% of the water in that frog's body turns into ice. Not chilled. Ice in masses in the spaces between its cells. While it's frozen, there's no heartbeat, no blood circulation, no breathing, no brain activity, no movement. By almost every measure we'd normally apply, the animal is dead. Can stay that way for 6 months or more. And in spring it thaws out, its heart restarts, and it hops away. Now, I'm not telling you this because it's a fun animal fact. I'm telling you because of what's happening inside its cells, and because the problem this frog has solved is a problem human medicine has not solved. Let me explain what freezing actually does to tissue. When ice forms in the spaces around cells, it does two things. It pulls water out of the cells, which shrinks them and concentrates everything inside. And it physically blocks circulation. Blood can't move through frozen tissue. No circulation means no oxygen delivery, which means the electron transport chain, the thing I talk about on this channel constantly, has nothing to hand its electrons to at the end. Researchers describe this directly. Freeze and thaw is an event comparable to ischemia and reperfusion. Those two words are worth knowing. Ischemia is tissue being cut off from blood supply. Reperfusion is blood flowing back in. That pair is what happens in a heart attack. It's what happens in a stroke. It's what happens to a donor organ between removal and transplant. And here's the thing that surprises people. In that sequence, a great deal of the damage doesn't happen during the oxygen shortage. It happens when the oxygen comes back. While tissue is starved, the electron transport chain backs up. Electrons accumulate with nowhere to go. Then oxygen suddenly returns, and all of those stalled electrons find a target at once. Instead of orderly transfer, you get a burst of reactive oxygen species. That burst is well documented in the reperfusion recovery period, and it's responsible for a substantial share of the real injury. So the frog isn't just solving a cold problem, it's solving a restart problem. Every spring, it performs a controlled reperfusion of its entire body. How? Several ways, and they're all worth knowing. First, cryoprotectants. As freezing begins, the frog's liver dumps enormous amounts of glucose into the bloodstream. Blood glucose reaches concentrations that in a human would be a medical emergency. That glucose floods into cells, where it lowers the freezing point inside them and physically limits how much they can shrink. Urea does similar work. Second, metabolic suppression. Rather than burning through its reserves trying to maintain normal function, the frog powers most things down. It shifts to fermentable fuels, accumulates lactate, and accepts a slow decline in ATP, rather than fighting it. Third, and this is the part you should care about most, it prepares its defenses in advance. Freezing triggers the frog to upregulate protective enzymes. Manganese superoxide dismutase, which handles superoxide inside mitochondria specifically. Catalase, which breaks down hydrogen peroxide. Glutathione, and the enzymes that keep it in working order. So when the thaw comes and that burst arrives, the machinery to handle it is already built and waiting. And there's a detail here that connects to a video I made last week. Among the genes the frog turns up during freezing are genes carried on its mitochondrial genome, specifically ATP6 and 8, ND4, and 16S RNA. If you saw the video about the second genome, that's what those are. Your mitochondria carry their own separate loop of DNA with 37 genes on it, and a subset of those build components of the electron transport chain. The frog is reaching into that second genome as part of its survival response, not just its main chromosomes, the ancient bacterial one inside its mitochondria. Alright, now I want to be careful because we've arrived somewhere that a lot of content would rush straight past. The frog survives oxidative stress using antioxidant defenses, and there is an entire industry built on selling you antioxidants. So let me draw the distinction sharply. The frog is not eating antioxidants, it's synthesizing enzymes. Superoxide dismutase and catalase are proteins the frog's own cells build, on demand, in response to a signal. They are catalysts. One enzyme molecule neutralizes target molecules over and over, continuously, in exactly the location it's needed. A dietary antioxidant is a molecule that gets consumed when it reacts. One for one. and it goes wherever the bloodstream takes it, not necessarily where it's required. Those are genuinely different systems, and conflating them is one of the most common errors in this space. So the useful question is, can you increase your own enzymes the way the frog does? And here the human evidence is actually good. Exercise training increases the expression of antioxidant enzymes in human skeletal muscle: superoxide dismutase, glutathione peroxidase, catalase. This has been shown across endurance, high-intensity interval, and resistance training. The mechanism is what's called hormesis. Exercise produces a moderate, temporary rise in reactive oxygen species. Those act as a signal, not just as damage. And your cells respond to that signal by building more defensive capacity than they had before. One group of researchers put it strikingly. They proposed that exercise itself can be considered an antioxidant because training increases the expression of classical antioxidant enzymes. Now the uncomfortable part, and I'd rather you hear it from me. If the signal is the reactive oxygen species, then blunting the signal may blunt the adaptation. There's research suggesting exactly that. The same group noted that lowering endogenous antioxidant enzymes through antioxidant supplementation may not be a good strategy when training. And there's animal work showing high-dose supplementation suppressing antioxidant enzyme activity and downregulating the transcription factor that controls those enzymes. I want to be measured about this. It's an active area, findings vary by dose and compound, and I'm not telling you every antioxidant supplement is harmful. What I am saying is that the intuition of more antioxidants equals less damage is too simple, and in some circumstances it may work against you. The frog's strategy is to build the factory. Buying the finished product is a different strategy, and it isn't obviously better. So today's free lever is exercise, but for a more specific reason than usual. It isn't only about capacity. It's the signal that tells your cells to build their own defenses, which is the same category of thing the frog does before it freezes. And where does my recommendation sit today? Deliberately narrow. CoQ10 is a carrier in the electron transport chain. It moves electrons between complexes so that ATP can be produced. Levels tend to decline as we age. You'll notice I'm not calling it an antioxidant today, even though you'll see it described that way. Given everything I just explained about signaling and adaptation, I'd rather stick to the claim I'm confident in, which is that it's a physical component of the chain. If you want to support that machinery, the link in the description below is an affiliate link to Mitochondrial, which is PQQ and CoQ10 with a 90-day money-back guarantee. And if you want more videos where an animal fact turns into a reason to be skeptical of a product category, subscribe. This video is educational only, and it's not medical advice. Talk to your doctor before starting new or more intense exercise, or before changing any supplements you take.